Last time we discussed black holes in context of Schwarzschild solutions. The tutorial will discuss the Schwarzschild solution in de Sitter space and in de Sitter space. Today, I'd like to discuss black holes in what's called semiclassical gravity. So, semiclassical has a technical definition here. By semiclassical, I mean I'm treating quantum field theory, I'm working quantum field theory in matter sector in a curved space-time. Yeah? Okay, we'll do. So this is the matter, but I'm treating the gravitational field classically. So part of my theory is quantum, the rest of my theory is classical. So I'm using this curved space-time as a solution to Einstein's equations. So people looked at this extensively in the early 1970s and discovered that black holes obey the laws of thermodynamics. So what I want to present to you today are the laws of thermodynamics as they apply to black holes. That's the goal of today's lecture. So, the laws of thermodynamics are familiar from your undergraduate education. And there's a zeroth law, which states that at equilibrium, the temperature of a system is constant. So, T is constant for systems at equilibrium. Now, there's a notion of temperature that you, or an analog of temperature that you associate to black holes. Now, the Earth, for example, has an equatorial bulge. What this means is that the gravitational acceleration when you drop something is different depending upon where you are on the Earth. It's roughly 9.8 meters per second squared, but the actual numerical value changes depending upon where you are. Now, for a black hole, the surface gravity, kappa, is constant everywhere on the horizon. This kappa is an analog of temperature of thermodynamic systems. And we'll see this explicitly. Okay? So, we'll see that the laws of ordinary thermodynamics have an exact analog for black holes. The first law of thermodynamics is essentially a statement of the conservation of energy. So we know that dE is TdS minus PdV plus UdN, for example. So what we're saying is there's a state function energy, it's a function of entropy, volume, and particle number, and we write this as dE is dE ds at constant v and n, ds plus dE dV at constant s and n plus dE dN at constant s and v dN. So there's a state function differentiating with respect to the variables that define the state function defined for us the temperature, the pressure, and the chemical potential. So it turns out that black holes have a similar state function which describes the area. So remember I told you yesterday that if we have the mass, the angular momentum, and electric charge of a black hole, this defines a black hole solution uniquely in Einstein-Maxwell theory. So the area is equal to 4 pi, I'm working in 4 dimensions, 2 g Newton squared m squared over c to the 4th minus gn q squared over 4 pi epsilon naught c to the 4th plus 2 g Newton m over c squared square root gn squared m squared over c to the 4th minus gn q squared over 4 pi epsilon 0 c to the 4th minus j squared over m squared c squared. So I'm being pedantic here. I'm putting in all the factors of c. There's a reason for this. Well, we'll see what the reason is shortly. So given these parameters, mass, angular momentum, and electric charge, the area is defined in terms of these parameters. This is the area of the event horizon of this black hole. So,
can you read out the square root?
j squared over m squared c squared. Gn squared m squared over c to the 4th. I'll distribute nodes, don't worry about it. It's just some function. Okay? It's not, the details don't matter. I just want to emphasize the area is a function of m, j, and q. This function can be inverted. We can write the mass as square root pi over a, c to the 4th, gn squared, area over 4 pi, plus gn q squared, 4 pi epsilon 0, c to the 4th, squared, plus 4 j squared over c squared to the 1/2. So you can do the algebraic manipulation to write mass in terms of area, charge, and angular momentum. Now, given this expression, we can write then dm is dm dA at constant j and q dA plus dm dj at constant a and q dj plus dm dq at constant a and j dq. This is just the same manipulation as we did in writing down the first law of ordinary thermodynamics. Okay, so we identify dm dA as, well, we do, since I'm keeping these factors around, we multiply this by expression by c squared, and I'll find this is kappa c squared over 8 pi g Newton dA plus omega dj plus phi dq, where omega is the angular velocity of the black hole and phi is the electric potential associated with this charge. Okay. So there's an exact expression for how the energy, the mass of the black hole changes if I change the area, if I change the angular momentum, or if I change the electric charge.
Sorry, what was kappa?
Kappa is the surface gravity. Okay? So this, we call this expression the first law of black hole mechanics. So the temperature of the black hole, we notice that this term formally looks like an expression like this. So identify surface gravity with temperature, noting the analogy that the surface gravity is constant everywhere. So because surface gravity is constant everywhere, we know the temperature is constant equilibrium, we identify TH, the Hawking temperature of the black hole, as H bar kappa 2 pi K Boltzmann C, and the entropy of the black hole as the area K Boltzmann C cubed for H bar GG. Now, I want to make a few observations here. The first observation is that if kappa equals 0, the temperature is 0. So kappa equals 0 is achieved for what are called extremal black holes. So for example, if you look at a curved black hole with angular momentum and mass, it turns out that the angular momentum is less than or equal to g Newton mass squared over c. When this inequality is saturated, when, in other words, J equals g Newton m squared over c, kappa vanishes. The black hole is said to be extremal. If kappa is not equal to 0, black hole is said to be non-extremal.
Does that mean that you won't get a chance to into the black hole at this point?
No, you'll still fall into the black hole. I mean, if you jump into the black hole, you're stuck in the black hole. It's just the surface gravity vanishes.
So what does that mean?
It means the acceleration of gravity is 0.
Which means you kind of pop it. You don't actually go.
Well, I guess. Okay. In any case, this temperature can be vanishing. So if something has 0 temperature, it means it's not. Well, these black holes with finite temperature radiate like a black body. At 0 temperature, it's not radiating, so it's a stable black hole at 0 temperature. So that's another observation I want to make. The next observation is these formulae denote the first appearance of H bar and K Boltzmann in the story. So K Boltzmann is just there for units. It's a dimension-full parameter in order to make entropy have units of K Boltzmann. So the K Boltzmann is not mysterious. The H bar is a statement that the effect of having temperature and entropy is quantum. It's because there's an intrinsic identification with the entropy with a set of states in our theory. So in ordinary thermodynamics, there's an underlying description in terms of quantum states. That's what you're counting with entropy. For example, the entropy of a gas in the room is the number of ways of arranging the gas molecules. And the entropy parameterizes our ignorance of what the actual arrangement of the gas molecules is. We're only concerned about the intensive variables like pressure and temperature, say, in characterizing the room. The entropy is where we hide away our ignorance about the actual quantum state. So the fact that H bar appears in the denominator says that the H bar goes to 0 limit, the entropy is infinite formally for a black hole. Okay. The other feature of the entropy, which is worth pointing out, is that the entropy scales like an area. If you consider the volume, if you consider extensive quantities in ordinary statistical physics, if you put the word extensive means that the entropy is at, and you have two non-interacting systems. So you have two different boxes of gas in the room, They're not interacting. The entropy of the total system is the entropy of one box plus the entropy of the other box. The entropy scales with volume, in other words. If you make the volume of the room bigger by a factor of lambda, the entropy rescales by a factor of lambda for ideal gas. Now, here, the entropy scales with an area. So it's not extensive in the sense that we knew entropy to be extensive in statistical physics. This is a characteristic difference in how we consider entropy for these systems. The entropy is one dimension less than what we naively expect. Okay? This is important. This is basically the origin of the principle of holography in quantum gravity. That entropy, the degrees of freedom you associate to a quantum gravitational system, is one dimension less than what you naively would expect.
What causes that, Vishnu?
What causes that is essentially the subject of a lot of research these days. There's good reason to believe, there are many examples we have in which we know that entropy is arrested by codimension 1 degrees of freedom. We don't have a general explanation for the origin of the principle of holography. I would like such a thing. I hope to see such a thing in my lifetime, but we don't have it today.
I just want to say some words about the gauge branch of gravity being so big. Restricts to restrict the boundary or these kind of things.
Well, yeah, you can say a lot of words.
A lot of words, but
There's no formal derivation of the principle of holography, but it seems to be a fact that gravitational systems, especially gravitational systems, for example, anti de Sitter space, the degrees of freedom of string theory on anti de Sitter space are exactly equivalent to a quantum field theory which lives in the boundary of anti de Sitter space. We see something similar happening in the matrix theory for M theory in 11 dimensions. We see that degrees of freedom are arrested by matrices which describe what's happening in directions orthogonal to a light cone. We see various examples of this holographic correspondence. We don't have an actual physical derivation of this. But again, as Costas was saying, this is related to the fact that gravity has a large gauge symmetry associated with diffeomorphism invariance of the theory. And by modeling out by this gauge symmetry, by this diffeomorphism invariance, you may be able to get a decrease in the number of dimensions to describe the actual theory. Black holes are the paradigmatic examples for studying this principle of holography. So, for example, we'll discuss what black holes have to say about this in the next lecture and a half. Okay? So, because we think about entropy as being characterizing the number of underlying quantum states in the system, I want to think about the number of states describing a black hole as E to black hole entropy divided by K bar. Okay, so we've discussed now the zeroth law and the first law of black hole mechanics. The next law is the second law of black hole mechanics. And this is a consequence that was first observed as a result of the weak energy condition. The weak energy condition in gravity tells us that if you take a time-like vector T mu, then T mu nu, T mu, T nu is greater than or equal to 0. So the weak energy condition. Okay? The weak energy condition implies the density, rho, is greater than or equal to 0, and the combination, rho c squared plus the pressure, is greater than or equal to 0 for a system in gravity. Given this weak energy condition, you apply this to a black hole space-time, and what you find is that the area of the black hole is a non-decreasing function in time. So again, this emulates the second law of thermodynamics. The entropy is a non-decreasing function in a physical process. But actually, this has to be modified slightly because the black hole lives in a broader space-time. And as a generalized second law, we apply to black holes. Generalized second law, simply the entropy of the black hole plus the entropy of the rest of the universe is a non-decreasing function.
What is T here?
T mu is a time-like vector.
Can you please repeat what you just said about this energy?
Okay, so the area of the black hole increases in any physical process. Actually, you want to interpret the area as an entropy in this manner, and you say the entropy of the black hole, the change in the entropy of the black hole, plus the change in the entropy of the rest of the universe is greater or equal to 0 in any physical process. So this is the analog of the second law of thermodynamics.
Sorry. Yeah. We require that the T mu be a future derivative, right?
Yeah. Yes. Yeah, you want T to be increasing, so you want dA dt greater or equal to 0 as T increases. So as a result of this observation, and coupled with this statement, it's tempting to take the entropy seriously and think of this as counting the number of states. Because that's what the ordinary second law of thermodynamics is telling us. Because of time evolution, we're seeing that generic state is, has more, the configuration space in quantum theory increases with time. That's what we're seeing in our universe, basically. And because we're seeing this everywhere in the universe, this is not a statement of the initial condition, it's a statement about physics. It's not that we're in a special situation in the universe in that things look irreversible microscopically because of this special situation we've engineered. This is a fact about the initial condition of the entire universe, if you like. Okay. Finally, there's a third law of black hole mechanics. Third law of black hole mechanics is that without violating energy conditions, we can't go from extremal, non-extremal to extremal. This is analogous to the statement that if you do a finite number of steps in some physical process, you can't reduce this temperature of your system to the absolute zero temperature. You can't reduce the entropy, in other words, to the degeneracy of the ground state you experience at zero temperature in statistical physics. So it's worth noting that even if kappa equals 0, even if the temperature is 0, the entropy can be a finite quantity, a large quantity. So this is another way in which black hole systems differ from thermodynamic systems we're familiar with, in that the entropy is, S can be large, even at T equals 0. Whereas for most ordinary systems that we encounter in the laboratory, for example, temperature equals 0 means the entropy is a very small number. Essentially, degeneracy of the ground state. Okay? Questions? Comments?
So the thermodynamics of the black hole is completely different from the usual thermodynamics that we know. Not, I mean, completely.
Formally, they're the same. Formally, you can write down laws that are a perfect analogy to thermodynamics you've seen. Formally, you identify the entropy of a black hole with the number of quantum states associated with a black hole. But there are some differences, and the entropy is not extensive in the normal way, and the entropy at zero temperature can be large. Also, another way black holes differ from ordinary systems. Suppose you take a gravitational system, and we discussed yesterday that if you make gravity stronger, the systems become smaller. So if you make gravity stronger in the solar system, the size of the orbits will decrease in size. We also saw yesterday that the Schwarzschild radius of a black hole is proportional to G Newton. So when you make G Newton stronger, the radius of a black hole increases. Black holes behave differently than you naively expect.
Sorry, Rich?
Yeah.
So does that mean for any type of black hole, whether it's spinning, charged, or whatever, the surface gravity is always the same?
Pardon?
So for any type of black hole, whether it's spinning or charged or anything, the surface gravity is always the same?
No, the surface gravity is some function of the parameters you put in.
Yeah,
So
but no, I'm just saying around on the surface, like 0.
everywhere on the surface gravity is the same. Everywhere on the horizon, the surface gravity is the same. That's what this is how we got the idea of equilibrium, and how we thought initially that thermodynamics has maybe some relation to black hole mechanics. Okay, so this maybe is a good place to point out a major puzzle. Suppose we take two states, psi 1 and psi 2, have the same mass, the same charge, the same angular momentum. These states, for example, have you have some shape associated to psi 1, you have some other shape associated with psi 2. You make gravity stronger and stronger and stronger. Eventually, these states collapse to a black hole. The black hole metric then is the same, because they've got the same mass, same charge, and the same angular momentum. So the black hole metric can't distinguish between whether the black hole formed through the collapse of psi 1 or through the collapse of psi 2. These are pure states that we prepared. For pure states, we know in quantum mechanics, it's a unitary theory. We know that I bar d by dt psi is equal to h psi. We know as well that if you're thinking about a time-dependent Hamiltonian, we know that we can think about psi at a time t as e to the I ht over h bar minus I here, psi at time 0. So we know how to evolve states unitarily. Unitarian quantum mechanics says the information about which state formed the black hole in the first place can't be lost. But the black hole metric is insensitive to any data except the mass, the charge, and the angular momentum. So the question we can ask is, how do we get this information about what formed the black hole in the first place out? The other way we can sort of phrase this is, okay, so we can interpret maybe the entropy of the black hole as our ignorance about which initial condition formed the black hole in the first place. That's a reasonable interpretation of an entropy you associate to a black hole. But quantum mechanics tells us that somehow there's a way to extract this information from the black hole. How do we do this? This is called the information paradox. And I want to discuss this information paradox in terms of the evaporation of a black hole and the Hawking process. So in quantum field theory, the vacuum is dynamical.
Sorry,
Yes.
is it because we are working in 40, then the M and J, Q only fix our space-time uniquely. But we saw yesterday that if we're not working in 4D, that is not the case. So I mean, I think in the 5D, for example, yesterday, that there is no kind of. So we will have definitely different.
There's a finite degree of non-uniqueness, though. I mean, there are three possibilities. It's either a fat ring, a thin ring, or a minus-parity black hole, given these choices. That doesn't really, I mean, the information problem, I think, exists in 8 dimensions. And 4 dimensions may be the simplest scenario because we have uniqueness. So, Heisenberg uncertainty principle, I want you to be careful about this uncertainty principle I'm writing because there's some subtleties that were pointed out by Hardoff and Bohm. But I won't go into these subtleties. Let's just take this idea for granted, that the uncertainty in the measurement of the energy in some period of time is bigger than or equal to h bar. Let's take that for granted. The energy, so the vacuum in quantum field theory is dynamical. You can imagine in very short periods of time delta t borrowing a lot of energy from the vacuum. So imagine there's a black hole and you pair create, say, an electron-positron pair in the vacuum. Electron-positron pair is together chargeless, so there's no violation of charge conservation or anything happening. But we're close to the black hole horizon. Let's assume that the electron has a momentum which takes us into the black hole. Classically, this electron can't escape. Momentum conservation tells us the positron goes the other way, off to infinity, where we're sitting collecting the radiation the black hole's emitting. And mass conservation tells us the black hole looks like it's losing mass. So we're collecting the positron. We notice this is a particle being emitted from the black hole is losing mass. You can equally interpret this as tunneling from the interior region to the exterior region. So, the black hole, suppose nothing is falling into the black hole. The black hole is radiating at a temperature TH. It's radiating like a perfect black body. And at infinity, as the black hole is emitting these particles, we're collecting the Hawking radiation. The black hole is getting smaller in the process because it's shedding mass. Okay? So the question is, can we recover the identity of the initial state that formed the black hole in the first place through an analysis of the Hawking radiation? Now, the black hole metric looks the same, irrespective of how the black hole formed. And the Hawking radiation process is because of the dynamic vacuum near the horizon, where the black hole looks the same, irrespective of how it formed. You might imagine that near the singularity, something funny is happening. The quantum gravity resolves, and the quantum gravitational resolution of the singularity is what captures the data about the initial state. That's a reasonable hypothesis to make. In this case, in this scenario, the Hawking radiation is really only sensitive to physics near the horizon. So we're really not probing the physics near the singularity. So this makes the problem of recovering black hole information from Hawking radiation very challenging. So, as well, these numbers for ordinary black holes are typically very tiny. So we know that for the Schwarzschild solution, kappa is c to the fourth over 4 g Newton times n. And this means the temperature is equal to h bar c cubed over 8 pi g Newton m k Boltzmann. For a solar mass black hole, this number, Hawking temperature, works out to 10 to the minus 8 Kelvin. 10 to the minus 8 Kelvin is approximately the lowest temperature we've ever produced in the laboratory. Okay, so this is a very, very tiny temperature. It's much, much smaller than 2.73 Kelvin, the temperature of the cosmic microwave background. Okay. So these black holes are emitting, but they're emitting very slowly because the temperature is very, very tiny. The evaporation process takes a very, very long time. Solar mass black hole takes longer in the age of the universe to evaporate, much longer in the age of the universe to evaporate. So this whole process of recovering information is complicated. But we expect, because of the unitarity of quantum field theory, there must be some way to recover this information. Okay. What time is it?
Almost a quarter.
Okay, so the next lecture, I'll present some string theory description of what these microstates might be and how sketch out a heuristic picture for how to recover the information from a black hole. I'm going to do a mathematical aside now, which I'll leave in the next lecture, and this is sort of a self-contained little topic today. Okay? So, I want to discuss how to count. In particular, I want to discuss how to partition a large integer into smaller integers. So, let me define P of m, q to the m equals 0 to infinity. And P of m are the number of ways of partitioning an integer m into integer parts that are so positive integers. Okay? So for example, suppose I wanted to partition the number 7. Or make it easier on myself. Let me partition the number 5. Okay, I can have 1 plus 1 plus 1 plus 1 plus 1. That sums to 5. I can have 1 plus 1 plus 1 plus 2. That sums to 5. I can have 1 plus 1 plus 3. That sums to 5. I can have 1 plus 2 plus 2. I can have 1 plus 4. I have 2 plus 3. I can have 5. Okay? Those are the 7 integer partitions of 5. So P of 5 is 7.
Sorry, but what's Q?
Q is just some parameter. I want to construct some Taylor series for some function such that the coefficients of the Taylor series are the partitions of n. Okay? So how would I go about doing this? What are the properties of this putative, what's the right-hand side? Well, one way to construct the right-hand side, this is Euler's construction, is to look at 1 plus q to the first plus q to the 1 plus 1 plus q to the 1 plus 1 plus 1 plus dot 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 times one plus q squared plus q to the 2 plus 2 plus q to the 2 plus 2 plus 2 plus dot 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 for 3, 4, 5, etc. And you can see that there's a term here with 5 ones. That contributes to the q to the 5th term on the left-hand side. There's a term here that comes from multiplying q to the 1 plus 1 plus 1 times q squared. That also contributes to the q to the 5th term. That's this term and that term. Q to the 1 plus 1 times the q cubed term for the next term here will contribute. So in this way, we see this right-hand side recovers the expression on the left-hand side. Okay? We can write the right-hand side as the product from n equals 1 to infinity of 1 plus q to the n plus q to the 2n plus dot dot dot. So that's what each of these terms are. Now, what's this? This is a geometric series. So we can write the geometric series as 1 over 1 minus q to the n. So this product, the Taylor series of this product gives us the partitions to n. This is a result due to Leonard Euler. And he stared at this for a very long time. And he worked on this for about 10 years, this problem. Well, I mean, he got this pretty quickly, but he worked on figuring out what the right-hand side meant for about 10 years. He was able to prove the theorem. This theorem is called the Pentagonal number theorem. And he ended up finding a closed form expression for the reciprocal of the right-hand side. So he found the product, n equals 1 to infinity, of 1 minus q to the n, equals the sum, k equals minus infinity to infinity, of minus 1 to the k, q to the gk, where gk are the generalized pentagonal numbers. So basically, you take a pentagon, and then you assign, so pentagon's a 5-sided figure. You assign points to the edges of the pentagon, and you count how many points there are. And you find that gk equals k, 3k minus 1 over 2 for positive k counts the number of points. So you have a pentagon. Next term, there are 5 points, another pentagon, you put points on the edges as well, count the number of points, you continue in this manner, and you get numbers that are determined for us by this function, where k is positive for these pentagons. The generalized pentagonal numbers allow you to have negative k. Okay? So bringing this to the other side of this equation, you end up with the formula that sum k equals minus infinity to infinity of minus 1 to the k, q to the gk, times the sum from m equals 0 to infinity of p of m, q to the m, equals 1. Okay? So, this pentagonal number theorem, which is a special case of the Jacobi triple product formula for theta functions. So there's this is sort of why q is being used. It's an elliptic variable in the end of the day. So this is one of the this is one of the origins of elliptic number theory. So we have this formula here, and it turns out that this formula lets us write p of n for any partition of n as the sum from k equals minus infinity to infinity of minus 1 to the k minus 1 p of n minus gk. So Euler found a recursive formula to describe the partitions of n. And in fact, Mathematica, for example, when it computes partitions of n, uses this formula. This is still the most efficient algorithm for computing the partitions of n, this recursive formula for them. So why do I mention this? I'm interested in the behavior of this function, p of n, in the limit where n is large. So in the 20th century, beginning of the 20th century, in one of the most romantic stories in the history of mathematics, Ramanujan went to Cambridge. And in the partition problem, Ramanujan and Hardy found the mathematical problem worthy of their genius. And they derived the expression that at large n, p of n goes like 1 over 4 root 3 n e to the pi square root 2n over 3. This is the asymptotic behavior of the number of partitions with an integer n. Witwatersrand in the 1940s found a convergent closed expression for p of n, but it's sufficient for us to just look at the Hardy-Ramanujan expression. Let's take a logarithm of this. The logarithm, log p of n, goes like pi root 2n over 3 minus log 4 root 3n. So this is a polynomial growth in n. This is a logarithmic growth in n. So this is approximately, we can bring the 2 out to get 2 pi root n over 6. It's actually multiply the top and bottom by square root of 2 to get this. And this is subleading compared to this term. For some reason, the name Carlys formula has stuck to this expression. But this is really the Hardy-Ramanujan Witwatersrand expression for p of n. So if you're counting things at large n, for example, if you're counting the behavior of harmonic oscillators at large n and deciding how to split the energy of the harmonic oscillator among the available levels, you may use this formula like this. It turns out this formula is a formula that's going to be crucial for us to describe black hole entropy. Okay. Any questions? Yeah.
And you mentioned the name of Ramanujan there. What was his contribution?
Ramanujan had an affinity with numbers. He had this ability to find very clever, very cute formula, especially involving infinite partial fractions or the way this behavior, this function is, for example. So Ramanujan wrote a letter to a lot of mathematicians in the United Kingdom describing his results. And most mathematicians he sent a letter to didn't take them seriously. Hardy looked at the formula that Ramanujan sent in his letter and noticed that some of the formulas are known in the literature, some of the formulas he could probably derive, and some of the formulas were astonishing. The astonishing formulas, he thought, were so imaginative, so creative, they had to be true, because no one could come up with something like this if it wasn't true. So Hardy brought Ramanujan to Cambridge, and Hardy and his collaborator Littlewood and Ramanujan collaborated during several years when he was in Cambridge. And it was one of the most productive collaborations in the history of mathematics. It revolutionized number theory. And this is one of the prime results of that collaboration. So, I get a lot of spam from people who claim to solve the universe in their model. And I sometimes wonder whether I'm making the same mistake as these other mathematicians in the UK did in ignoring genius. I think I'm not. I think most of the messages I get are crackpot messages. That's probably what happened in Cambridge. These guys, other people received letters they threw away because they looked like someone was talking to me about analysis or whatever crackpot things about partitions, emails. The party took this fellow seriously, and it was very productive mathematically and nice words.
Sorry, I think I missed the part where the number of partitions of integer is relating the formula of this present entropy of full flash.
We haven't gotten there yet. You didn't miss anything.
Oh, okay.
That's subject to next lecture. I just want to present this formula because I'm going to be using this formula later.
So, I missed that part of partition of it where you write out as 1 plus q1 plus q.
So what I did was I want to come up with some generating function such that the Taylor series, the generating function, has coefficients, which are the partitions of the integers n. So for example, suppose we look at the partitions of 5. How many ways of getting 5 are there on the right-hand side? I can take the term with 5 ones in here, and then multiply by 1, etc. on the other terms. That's this partition here. Suppose we want this partition. I would extract this term from the first expression, extract this term from the second expression, extract 1s from all the remaining terms. Suppose I wanted this expression. I would start with this, and then the q cubed term from here. So all of these partitions can be expressed as a unique product of one term from each of these expressions.
Would you ever substitute the value for q, or is that not possible?
As I said, q is related to elliptic curves, so you end up sometimes substituting values for q when you're studying elliptic curves. Other questions? Okay, we'll take a break.